We start our exploration into a long chapter regarding exponents, polynomials, and all the different ways that we can manipulate those by taking a look at exponential expressions, which make up the bulk of our polynomials. Exponential expressions are just that, expressions that contain exponents. Our base, it can be a numerical value, or it could be a variable, or it could be a combination of them. The base is the factor for repeated multiplication, and the exponent is the number of times the base will be repeatedly multiplied. Therefore, 5 to the third power represents 5 being multiplied by itself 3 times, while y to the 6th power represents y being multiplied by itself 6 times. We have a few different rules that we follow when we're applying different operations to polynomials and for exponential expressions. The first is the product and quotient rule. So let's review multiplication and see how we can apply that to the rule that goes for exponential expressions. If we have x to the second power and x to the third power, remember that is x times x times x times x times x. So x to the second times x to the third. Well, we see that we have x being repeatedly multiplied 5 times. So that is x to the 5th power. We can get this same result by applying our product rule, which says when we are multiplying two exponential expressions that have the same base of x, then what we can do is just keep the base and add the exponents together, which gives us the x to the 5th power, and that's the rule that's indicated here. When we have the same base, we add the exponents. Notice also, if we have a coefficient, we can go ahead and multiply those coefficient factors together. So let's go ahead and simplify these, and but we're not going to evaluate it if we have a numerical base. So here we have a base of 2, and we're taking 2 to the 2nd power and 2 to the 5th power. So if we were to write it out again, we have 2 times 2 times 2 times 2 times 2 times 2 times 2, which is 7 times, 2 to the 7th power, which again is the same as just taking 2 to the 2 plus 5th power, which equals 2 to the 7th. So using our shortcut, we have x to the 7 plus 3, which equals x to the 10th. Here we have 3 different bases, or 3 different expressions, but since they all have the same base, we can go ahead and just add all of the exponents at once, giving us y to the 7th power. Here we have numerical coefficients as well, so using our product rule, we can go ahead and multiply the numerical coefficients, so we can have 3 times 5, and with x to the 6th power times x, we end up getting x to the 6th plus 1, so it is 15x to the 7th. We have multiple variables, multiple bases, and coefficients, so we'll multiply the numerical coefficients together, and we have x to the 3rd times x, p to the 2nd times p to the 10th, so we end up here multiplying, and we get negative 9.6 x to the 3rd plus 1, p to the 2nd plus 10, negative 9.6 x to the 4th, p to the 12th. Now we can apply similar logic to our power rule. Let's think about division. Let's expand this out again. So we have x 9 times, x to the 9th power, divided by x to the 2nd power. Well, when we have common factors in our numerator and denominator, we can eliminate those factors. But I still have 7 x's left over, x to the 7th power. This is the same as taking x to the 9th minus 2, taking the 2 exponents and subtracting them for our quotient rule, leaving us with x to the 7th. And so we see that step here. If I have the same base, I can take the exponents and subtract them, and then any integer coefficients we can go ahead, or any real coefficients, we can go ahead and divide those as normal, or simplify the fraction. So using our quotient rule, we have x to the 7 minus 4, which is x to the third. We have 5 to the 8 minus 2, which is 5 to the 6th. Here we have our real coefficients, so we'll divide those, and we'll do x to the 6 minus 5, so that gives us 5x. Here we have 12 over 14. We'll simplify that to 6/7, and we have y to the 10 minus 8, z to the 7 minus 7, which gives us y to the second, z to the 0. Well, let's go ahead and come back to this for a second, and let's look at our zero exponent rule.